Hello, this video looks at finding a linear relationship between two sets of data. We find the equation of a best fit line. This technique can be applied to an experimental set of data that appears to follow a linear pattern. I'm Seamus Bellew, and this video is for first year science and electronics students at DKIT in Dundalk. So here, in this example, this set of data applies to a particular patient. Some of us would be aware of the adjustment of medication for those who need to have their blood thinned from time to time. The medication is determined by constant monitoring and is specific for each patient. So this example here would apply to a particular patient. So we have 5 different examples of the amounts of medication that the patient would have taken and the effect that would have on their pulse rate. So for example, if the patient had been given 12 micrograms of the drug per litre, their pulse rate came down to 66 beats per minute. So obviously there's some kind of an optimum pulse rate for the particular patient. So here we see the graph of X plotted against Y. So you have the various drug dosages, and for example, if the drug dose is 8, the pulse rate is 76. So you can see at that stage it's still a bit high, so possibly it might need to come down a wee bit with medication. So the 5 different points are plotted on the graph page, and this is what we call a scatter graph. So on the x-axis we have the drug dosage in micrograms per litre, and on the y-axis we have the pulse rate in beats per minute. And we're looking to find the equation of the best fit line that fits this data, and the equation of that line is going to be y equals mx plus c. So another name for the finding of a best fit line is it's called the least squares line. It's also called the regression line, and we're going to use the best fit line. Now here what we're doing is, because the beats per minute under 50 are not being utilized, we reduce the graph page and zoom in on the particular area of interest. So essentially we just have this here representing the x-axis, and we have a kind of a zigzag, and then we start the y-axis at 50 because they're the relevant value. So we look at this zoomed version. Here we're looking at an example of maybe what the best fit line might look like. We know the line won't fit on all the points because the line doesn't fit perfectly. But in the best fit line, you're aiming to get the perpendicular distances on each side to sort of match up. So in a rough sense, that distance there roughly is the combined sum of those distances, and that's why it's called the least squares line. But we're going to continue to call it the best fit line. Now, before we go into the details of how we get the best fit line, we're going to do a small bit of statistics, and this is background then for finding the equation of the best fit line. So supposing we have 5 family members and their ages are 8, 10, 12, 14 and 16, and we ask a very simple question: what's their average age? So all we do is we add up the 5 numbers, 8 and 10, 18, 12, 30, 14, 44 and 16 adds up to 60. And to get the average we divide by 5 because there are 5 family members. So the average age of this particular family of 5 members is 12 years. And here's the notation that we're going to use. The average, we call it x bar, is equal to the sum of the ages. That symbol means the sum. It's the sum of the ages. In this case, the sum of the ages is 60, and we divide by the number of family members. And here the number of family members is 5. So x bar, which means the average or the mean age, is equal to 12. Now let's look at a second family. Well, it's slightly unusual, but anyways, the ages of all the members are 12. And again, if you add up the 5 12s, you get 60, and you divide by 5, so the average age is 12 again. Here's another set of family members. So these 5 members, the ages range from 4 to 20, 4, 6, 12, 18, 20. Again, add up the ages, 10 and 12 is 22, 18, 40, and 20, 60. The average age is 12 years. So you can see we have 3 different sets of data, so 3 sets of families, let's say, and the figures are sort of doctored, and you notice that the average age is the same in each occasion. So no problem with finding the average. But if I was to tell you 5 family members have an average age of 12, you would hardly guess that they all have the same age. That's very unusual. So why do we do 3 sets of data? And you can kind of see that this set of data here, that they're all the same, exactly the same as the average, not spread out at all, no variation. This set of data seems to have some variation about the mean, about the 12, and this set of data here has more variation. 4 is much further from 12 than, let's say, 8, and 20 is much further. So basically, while the 3 sets of data have the same average, the amount of variation going on in them, the amount of variation from the mean or the standard deviation differs, and now we want to look at that statistic as well. So what we're going to do is we're going to look at what's called the variance of each of these sets of data. The average is the same, but the variance or the standard deviation is going to be different. So what do we mean by the variance? So looking at the first set of family members, the average age is 12. X bar equals 12. So to find the variance, all we do is we take each age, we call that the corresponding X value, and we get the difference between the age and the average age. So if we take the first age there, 8, 8 take away 12 is minus 4. So X minus X bar. So the first age, take away 12. The next age is 10. 10 minus 12 is minus 2. And so on. 16 minus 12 is equal to 4. So these are all the differences. So we take each age in turn, take away the mean, so get the difference. Now, if you add up these ages here now, these differences, we have minus 4 minus 2 is minus 6, 2 and 4 is 6, 6 and minus 6 is 0. So that 0 would lead you to contend that there wasn't any difference or any variation. But you can see there's negatives cancelling out positives. So in order to prevent the negatives cancelling out positives, we actually square this quantity. So when you square the values, it'll be X minus X bar, the differences between each age and the mean, all squared. So minus 4 squared will give us 16, 4, and so on. So we squared the data. Now we won't have the problem of minuses cancelling out pluses. So what we're going to do to get a handle on the variance, we're going to kind of add up the sum of the differences. Now they're differences squared. So 16, 4 is 20, and 4 and 16, another 20. So the total of the differences is 40. The difference is squared. So we add up the differences and we get a total of 40. And then what's the average? So 40 divided by 5, there's 5 family members, and we get 8. So we assign the number 8 to the quantity that we call the variance. So basically, just take the ages, get the difference between the mean, and then square it to prevent positives cancelling out negatives, add them up, and divide by 5, and we get the variance to be equal to 8. So you might have done this in school. And then what we do is we take the square root of the variance, and this gives us the standard deviation. And the square root of 8 is equal to 2.83 years. So we say this set of data has a variance of 8, and the standard deviation is 2.83 years. So the standard deviation kind of measures how spread out the data is about the mean. Now somebody might say to me, couldn't we just made all these positive? 4 and 2 is 6, and 6 is 12, and divide the 12 by the 5, and we'd have got 2.4. That would be a kind of a measure of deviation, but there are other reasons in statistics why we square this difference and then divide by 5. We won't go into that today. So the normal way of finding standard deviation is you get the average, you get the difference between the age and the mean, and then you square them to prevent the positives cancelling out the negatives. In this case, add them up and divide by the number of family members, 5 in this case, and we get 8. So the variance is 8, the standard deviation is 2.83 years. So we'll apply this process now to the other two. So once again, just to emphasize that when you have the variance, in this case 8, to get the standard deviation, you take the square root of 8 to get the standard deviation. The taking of the square root kind of cancels out the square that we put in earlier on. We put the square in to prevent positives cancelling out negatives. So in order to undo that square later on, we take the square root of our final answer, the variance, to give us the standard deviation. Data. So there's the first set of data. The variance is 8, standard deviation 2.83. So again, looking at the next set of data, again the ages, and take the differences. The average is 12, the difference between 4 and 12 is minus 8. Next one is minus 6, 0, 6, 8. And then to prevent the positives cancelling out the negatives, square them again. So we get 64, 36, 36, and 64. And adding all that up, we get 200. And 200 divided by 5 is equal to 40. So the variance this time is equal to 40. The variance is higher this time. We knew that because 4 is much further from 12 than in the previous set of data. Okay, so the variance is 40, and then we take the square root to get the standard deviation. Standard deviation is square root of 40, 6.3 years. So this is kind of somehow a measure of how spread out this data is about the mean. So the standard deviation is 6.3 years. So 6.3 kind of somehow represents how spread out the data is in that example there. So feeding that information back in, the variance was 40 for that set of family members, standard deviation 6.3. And we don't really need to do this one, but just to clarify, there's no variance between each of those ages and the average age of 12. So it's going to be 0 and 0. But let's just check it out, just for completeness. 0 is the gap, and there's no difference squared either, divided by 5. So the standard deviation is the square root of 0. So it's all 0. There's no deviation. There's no variance. And that kind of typifies what we're trying to illustrate here. So now comparing the three sets of data. Each set of data has the same average of 12 years, but the variance or the standard deviation gives us another bit of clarity about each set of data. So the lower the standard deviation is, the closer all the values will be to the mean, in this case 12, and that's as close as you come. There's no standard deviation. The standard deviation in this set of data is relatively close. It's only 2.83 years, whereas in this one the standard deviation is much higher. So we're going to use this technique of finding the average, the variance, and the standard deviation for the situation of finding the equation of the best fit line. So let's just do one more example. This is a different example of 5 family members. The ages are different this time. The ages are 8, 12, 8, 10, 12, 14, 18. Add up the 5 ages, we get 62. Divide by 5, so the average is 12.4 years. So x bar is the symbol for the average. X bar is the sum of all the x's, in this case 62. Divide by 5, so the average age is 12.4. But now we want to find out the variance. So remember what we did the last time. To get the variance, you take each age and get the difference between the age and the average. So 8 minus 12.4 is going to be minus 4.4, minus 2.44, and so on. So let's just bring up those differences. And again, we'll square them to make sure positives don't cancel out negatives. So there we go. There's the differences. And now we square these to prevent positives cancelling negatives. So the gap between 8 and 12.4 is minus 4.4. Square it and we get 19.36. Likewise with 2.4, it's minus 2.4, but square it, 0.4. Then 14 minus 12.4 is 1.6. There's a difference when you cross over in the number, when the age becomes higher than the average. So the difference there is 1.6. Square it, 2.56. 18, take away 12.4, 5.6. Square that, you get 31.36. So add up all those squares, the squares and the differences. We get 59.20. Then we divide that by 5 to get the average of this variation squared. And we get 11.84. So the variance in this case is going to be 11.84. So our average is 12.4 years. Our variance is 11.84. And then to get a measure of how spread out the data is, we take the square root of the variance. The standard deviation is the square root of the variance, and that's 3.44 years. So we say the standard deviation is 3.44 years, and it kind of measures how spread out the data is. We'll come back to this set of data again. Now, to calculate the variance, there's an easier way to do it, but it's not as intuitive as to what the variance means. So the purpose of this method is just purely to calculate the variance. We know the answer to this set of data already, and you understand how the variance works. You take each of the ages and you get the difference between the age and the x bar. Then you square that and you add them up and so on. But this is another way to do it, and it's easier. So all you do is you list out the x numbers, the ages, and all you do is you square each age in turn. So 8 squared is 64, 10 squared, 12 squared, 14 squared, 18 squared is 324. And just add up the square of each of the edges. So the sum of the edges is 62. The sum of the x squareds is 828. And what we so from the last slide, we took all the x values, we added them up, we got the total of 62. So the sum of the x's is 62. And to get the average, we divide 62 by 5. So x bar is 12.4. Then on the last slide, for the x squared values, we added up all the x squared values and we got a total of 828. So the sum of the x squared values is 828, and divide that by 5 to get the average of the x squared values. So 828 divided by 5 is 165.6. So x squared bar is 165.6. So that's kind of a formal way of writing up what we did. X bar is the sum of the x's divided by the n. 62 divided by 5 is 12.4, and the mean of the x squareds is the sum of the x squared, 828 divided by 5 is 165.6. So now we're in a position to calculate the variance using this easier method. And the formula is given by Q1 equals the mean of the x squared values minus the square of the mean. So let's look at that now. So it's 165.6, take away 12.4 all squared. So that's going to give us the variance. And then looking at the detail on that, that's 165.6, take away 156.76, and that's equal to 11.84. So the variance for these x values is 11.84. This is the value we had before, and take the square root to get the standard deviation to give you the spread of the data. So this is a slightly easier way to calculate variance, and we're going to use this now in the equation of the Bestfit line. So again, just bringing it all together, our variance is 11.84, and our standard deviation is the square root of 11.84, which is 3.44 years. So we'll actually come across this data again in the context of the Bestfit line, and you'll remember that the variance for that set of data was 11.84. So here we are. We now know how to find the average of a bunch of data and the standard deviation. So if you notice the x data, we've already worked on that x data there. We found the average of the ages in the family, but now we're going to reassign the figures to correspond to the drug dosages. And we also found the variance of the drug dosage. So you know how to do that. Likewise, we do the same with y, and we'll find, in fact, we're going to find the averages of a number of set of data and another variance as well, but we'll come back to that. So our task in hand is to find the equation of the line that best fits these 5 data points, and that's an example there of a possibility of the best fit line, or it's also called the least squares line, where the distances on both sides are kind of matched, perpendicular distances. So again, to set the scene, we want to find the equation of the best fit line. It's also called the least squares line. It's also called the regression line. The equation of the line is going to be y equals mx plus c. M is the slope of the line, c is the y-intercept. So here's the data for the particular patient. So what we're going to do is we'll calculate the slope m and the intercept c, and then we'll have the equation y equals mx plus c. So we build this up gradually. So what we do is we make headings. We take the x numbers, we find the average of those. We take the y numbers, we take the average of those. We take the x squared numbers, we take the average of those. Likewise, we take the y squared numbers, take the average of those. And we also take the x times the y numbers and find the averages of those. So, and then we find what we call the variances. We've already done the x ones. The variance Q1 is equal to the average of the x squareds, take away the square of the averages. So that's the Q1 done in the x's. Likewise, we do the same on the y's. So you'll be given these formulas anyways. Students generally like working with these formulae. It's just a matter of kind of plugging numbers in. So the second variance is to do with the y figures, and that's to do with the beats per minute, the pulse rate. So the second variance is the average of the y squared numbers, take away the square of the average of the y's. The third variance is the xy, the average of the x times the y numbers, take away the average of the x's times the average of the y's. We'll come to this and you'll find it easy enough. Then you get the slope. Slope is equal to Q3 the third variance divided by the first variance, and then the intercept is C equals the average of the y's minus m times the average of the x's. We've already worked with this formula earlier on when we were doing the linear relationships. So again, here's our data, our 5 data points. We want to try and find the equation of the best fit line that fits them. So our first task is to go off, get the x numbers, get the average of those, get the y numbers, do the average of those, the x squareds, average of those, y squareds, average of them, and the x times the y. So let's build up a little table. So here we are. We already have the x numbers, they're given to us. They're the drug dosages that were given to the patient in different amounts. So 8 micrograms per litre and so on down to 18. And the corresponding beats per minute. So if the drug dose was 8 micrograms per litre, the beats per minute was 76, the pulse rate. If there was a high dosage, you can see that the pulse rate drops. So obviously there's an optimum drug dosage in here in the middle for the particular patient. So we have the x numbers, we've got the y numbers. And what we want to do now is to get the x squared numbers. So obviously 8 squared gives you 64 in that first row. 76 squared gives 5776. And then the xy, all you do is you multiply 8 times 76. 8 times 76 gives you the corresponding xy number. So maybe we'll just look at the row that contains 12 and 66. What's x squared? It's basically 12 12s, 144. The 66, the y squared will be 66 times 66, and the xy will be 12 times 66. So let's just look at that in a bit more detail. So what we're doing is 12, x is 12, y is 66, x squared is 12 times 12, what we said, and that comes out to be 144. So that's why 144 is listed in there. Likewise, 66 by 66 is 4,356. And that's why 4356 is in there. And finally, we do 12 times 66. The x number times the y number gives us the corresponding x times the y number for this row here. And that's 792. So stripping all that away, you can kind of see where these numbers come from now. So if x is 12, x squared is 144. If y is 66, the y squared is 4356, 66 squared. And the xy number is 12 times 66. 792, and we just repeat the operation for the different rows there as well. So we just fill up those details now and you can check them out. Our next task in hand then is we've got the tables now. We've got the x numbers, the y numbers, the x squared numbers, the y squared numbers, the x times the y numbers. And the next thing we do is we total up each column of numbers. So that's the symbol for the sum or the total. So the total of the x numbers is 62. The total for the y numbers is 338. The total for the x squareds, 828. The total for the y squareds, 23,012. The total for the xy's, 4,096. So we have our 5 different sets of data there. Our x numbers, our y numbers, x squared numbers, y squared numbers, x times the y numbers. And we get the totals of them. And now to get the averages. So to get the averages, we divide by 5. It's a bit like having the 5 family members. So to get the average of the x values, which we've already done, you've seen these figures before for the x. The average of the x numbers is 62 divided by 5. And that gives us 12.4. So we say x bar equals 12.4. That's the average of the x numbers. Likewise, the average of the y numbers, 338 divided by 5. So we say y bar is 67.6. That's the average of the y numbers. Likewise, the average of the x squared numbers. You've seen this x squared number before. So the total of the x squared numbers was 828 divided by 5. So the average of the x squared numbers was 165.6. Likewise, for the y squareds, divide the 23,000 number by 5 and we get 4,006.4. And finally, the average of the x times the y numbers is the 4,096 divided by 5, which is 819.2. So now we've got our 5 averages. So we can kind of relax now. We've kind of finished that data there. We just proceed now to use these averages to get the variances. So there's the averages done. So we next concentrate on these 3 variances, Q1, Q2, and Q3. We have already done Q1 earlier on, but let's do a recap on it again. So to get Q1, it's the variance of the x numbers And the formula for that is x squared is the average of the x squareds, 165, take away the square of the average, 12.4. So 165.6, take away 12.4 all squared, and that gives us the result of 11.84. So we saw that figure earlier on. So now let's do the same for the y numbers. So what's the variance associated with the y numbers? And that's the beats per minute, the pulse rate of the patient. So Q2 is the square of the y numbers, the average of them, which is the 4,000 number. Take away the square of the average of the y's. So let's take away 67.6 squared. So 4602.4, take away 67.6 all squared. Again, it's 4,000 number, take away 4,569.76, and we get that Q2 is equal to 32.64. So that's Q2. And then the third variance we get is to do with the XY. So Q3 is equal to the average of the XY numbers, take away the average of the X's times the average of the Y's. So that's 819.2, take away 12.4 times 67.6. That's 819.2, take away 838.24. That gives us a negative number. So Q3 is equal to minus 19.04. So we've got the three different variances. So we can just group them together now, and we'll proceed now to conclude the calculation of the equation of the best fit line. So let's just bring those three variances together. Q1 again was 11.84. That's the variance on the X numbers. Q2 is 32.64. That's the variance on the Y numbers. And Q3 is minus 19.04. And that's the variance on the X times the Y numbers. So we take those three variances now and we transfer them on to the next slide. So, nearly getting now to find the equation of the best fit line. First of all, we found the averages of the various sets of data. So the X, the Y's, the X squareds, the Y squareds, the XY's. Then we found the three associated variances. And we're now in a position to find the value of the slope for the best fit line and the intercept for the best fit line. So the slope M is Q3 over Q1. So divide the variance Q3 minus 19.4 divided by the variance Q1 11.84. And that gives us an answer of minus 1.608. So that's our M value, the slope of the best fit line. Then to find the intercept for the best fit line, the formula is C equals the average of the Y numbers, Y bar, minus M times the average of the X numbers, so minus M X bar. So C is equal to the average of the Y numbers, 67.6, minus M, and M is minus 1.608, times the average of the times the average of the X numbers, and the average of the X numbers is 12.4. That's why that's 12.4. So calculating all that, 67 minus minus is plus. So 67 plus 1.6 times 12.4 is 87.53, and that's equal to C, and that's the intercept for the best fit line. So finally, the equation of the best fit line is y equals mx plus c, where m is the slope that we calculated, minus 1.608. C is the y-intercept, 87.53. So the equation then for our best fit line is y equals minus 1.608x plus 87.53. So x stands for the amount of drug taken by the patient, and that's measured in micrograms per litre. And y is the pulse rate in beats per minute. So theoretically, if the patient didn't take any drug, y would be equal to 0 plus 87.53. So the pulse rate would have been 87.53 beats per minute, which is quite high. So it's obvious why this patient will be on some medication to lower that pulse rate down to the more normal, somewhere around 72, somewhere in the 70s. So we're going to bring the graph up now where the 5 points, the 5 original data points are, and we're going to try and plot the best fit line. So to plot a line, or to draw a line, we need 2 points. So let's keep this very simple. So let's take the x value. If x is equal to 0, y is equal to 87.53 beats per minute. So just put 0 in for x, so y is 87.53 beats per minute. And then we just take the value at the extreme right of the graph. If x is equal to 18 micrograms of drug per litre, y equals minus 1.608 times 18, put 18 in for x, plus 87.53, so y is equal to 58.6 beats per minute. So again, obviously for this patient, taking 18 micrograms per litre of the drug would be too much. So there's the 5 data points. We call that a scatter plot, and we're going to plot the line now. So we just plot these 2 points. If x is 0, y is 87.53, and if x is 18, there's 18, and the y is 58.6, just more or less under that red dot there. So there's the 2 points plotted now. So there's the 2 points plotted, and then we just join them up, and that there now is the best fit line, and the equation of it is y equals minus 1.608x plus 87.53, and you see some of the points are on above the line and some of them are below. So roughly that distance and that distance there, I know they look close, but there is some distance, and they roughly correspond to the distances on the other side. We also said this line is also called the least squares line. It's also called the regression line. Okay, so now here are some applications then to the best fit line. So this particular example, calculate the expected pulse rate if the dosage is 15 micrograms per litre. We could also ask, explain what the slope of the best fit line means in terms of the pulse rate and the drug dose. Estimate the dosage given if the pulse rate was 66.8 beats per minute. And the last part then is calculate the correlation coefficient that exists between the two sets of data. Is there a good correlation in this case? So let's just take a look at what we mean by the correlation coefficient, and then we'll come back and we'll answer the earlier 3 questions then as well. Okay, so the correlation coefficient is usually given by the letter R, and the formula for the correlation coefficient is R is equal to Q3, the variance Q3, divided by the square root of the other 2 variances multiplied, Q1 by Q2. So the correlation coefficient is denoted by the letter R, or the variable R, and there's perfect correlation when R equals plus or minus 1, and there's very poor correlation when R equals 0. So the correlation values in magnitude vary between 0 and 1. There's perfect correlation when all the points line up exactly on the best fit line. So it's a perfect line. So y equals mx plus c, all the points would actually be on the line. And this is an example of our line. Our line looks roughly something like that. That's our 5 data points there. And there might be good correlation. Let's say the R value is equal to minus 0.96. But we'll calculate that in a few minutes. So basically, the pulse rate depends on the drug dosage, and we're trying to form this linear relationship. So is there a good relationship between the pulse rate and the drug dosage? So is our model a good model? So that's another way of viewing that the data is well correlated, or there's good correlation between the Y data and the X data. So let's return to our questions. So the first one, calculate the expected pulse rate for a dosage of 15 micrograms. That's 15 micrograms per litre. So the X value is equal to 15 micrograms per litre. Substitute the X value in for X there in the equation of the best fit line. So Y equals minus 1.608 times 15 plus 87.53 equals 63.41 beats per minute. Second question, explain what the slope m means in terms of the pulse rate and the drug dose. M equals minus 1.6. So basically for every microgram of litre of medication administered, the pulse rate drops by 1.6 beats per minute. Estimate the dosage given if the pulse rate is 66.8 beats per minute. So this time the Y value is 66.8, substituting in for Y. So Y equals minus 1.6x plus 87.53, and that's equal to 66.8. So solving that equation, we get 1.608x equals 20.73. Divide both sides by 1.6, so x equals 12.9 micrograms of medication per litre. And finally, the correlation coefficient that we mentioned, to calculate it, R equals the variance Q3 over the square root of Q1 by Q2. There's 3 variances that we had before, so substituting them into the formula, R equals minus 19.04 over the square root of 11.84 by 32.64, and working out all that, we get an answer of minus 0.968. So there is good correlation as the R value, minus 0.968, is close or equals minus 1. So we hope you've enjoyed this video on the calculation of the best fit line for a set of data and some of the associated questions. So thank you very much.